Then we start today the last morning of this Valencia Metrica, and then the first talk will be begun by Professor Carlo Sinestrari from the Università di Roma Tor Vergata. It's a pleasure to have here the first time. And he will speak about Convergence results for volume preserving curvature flow.
Thank you for the introduction. Thank you, Esther, for the organization of this wonderful meeting and for inviting me. I'm happy to. The choice of the topic is volume preserving curvature flows, which I first become familiar with because of Esther, because I met Esther during her PhD thesis, which was about volume preserving flows. So it's a nice circumstance that that this was the room where she defended the thesis. So in this seminar, I will summarize different convergence results for volume preserving curvature flows. So partially recent, partially somehow older, maybe 5 or 10 years older, but I collect them because they have a common strategy of proof. So compared with the other talks on Ricci flow you heard yesterday, and I guess the following talks on mean curvature flow, this is somehow less ambitious. The results I will discuss will all deal with convex hypersurfaces becoming round, which is so somehow maybe the older problem which was considered in curvature flow. So I will not consider more complicated situations where there are finite time singularities. You have to understand the singularities with asymptotic profile and so on. So it will be convergence of convex hypersurfaces. And the general idea will be to for which situations we can prove a result similar to the classical Wisken one, that convex hypersurface converge to something round. And so I will first give some introduction, and then I will basically present 3 different results that with more or less a similar strategy. So I will give details on the first one, and I will quickly mention the other 2, which are more recent, but the strategy is clearer in the first example. I will discuss the volume preserving flow where the speed is a general monotone nonlinear function of the mean curvature. Typical example could be a power, but not necessarily power-like. Then, so restricting to the power case, I will discuss a recent result on the convergence of capillary hypersurfaces. So hypersurfaces in a half space with the prescribed angle condition on the boundary. And finally, I will mention a result on the fractional mean curvature flow. I will not give many details, but I will try to describe what fractional mean curvature flow, fractional mean curvature is, and the few things that are known until now about the flow. Okay, so I briefly recall mainly for the notation. So my evolving object will be denoted by M. It will be a hypersurface n-dimensional immersed in a n+1 Euclidean space. Nu will be the normal. Lambda 1, lambda n will be the principal curvatures. The H, capital H, will be the mean curvature. So you all know mean curvature flow. Every point moves towards with speed given by the mean curvature in such a way that the convex object contracts. And the interest is how general can we choose our speed? Can we choose a general symmetric function of the curvatures? Well, it's well known the main condition needed is parabolicity, so the monotonicity with respect to the curvature. And with this condition, this ensures the well-posedness of the problem, the local existence of smooth solutions. I will focus on the contracting case so that S is a positive function, at least on the positive cone, so speed which is contracting on convex surfaces. And since maybe the early times of the mean curvature flow, there is also this variant where one adds a second term pointing in the opposite direction, given by the average of the mean curvature. And in general, we can put general speed here and put the average of the speed here. In this way, if we consider closed convex hypersurface, the volume of the enclosed region remains constant. And this some basic properties. It's well known the usual mean curvature flow, which I will abbreviate with MCF, is the L2 gradient flow of the area functional. And also the volume preserving is a gradient flow, but considering only deformations with the fixed volume, fixed enclosed volume. And so on one hand, this may look nicer because looks more stable, but you soon realize that the presence of this non-local term has some unpleasant features. For instance, the avoidance principle is no longer true, so two hypersurfaces which start separate do not necessarily remain disjoint during the flow. For similar reason, an embedded hypersurface does not necessarily remain embedded. We will not see this phenomena in the cases I will consider because the convex case is easier. So convex usually, at least for the flows I will consider, remains convex and therefore also embedded. And but there is one thing which nice about volume preserving. This is the case of the mean curvature flow, but which is also observed since the beginning, that if you compute the evolution of the area, well, it's an easy computation. It's you find this expression, and using the definition of small h, you can rewrite this expression in this way, and in this way it looks very nice. You see that it is negative, well, less than or equal to 0, but it is only equal to 0 if h is identically equal to small h. So if you are on a constant mean curvature hypersurface or a stationary solution of the flow. Otherwise, there is a strict monotonicity of the area. As a corollary, since the volume is constant, then this quantity, this scale invariant quantity, which we can call the isoperimetric ratio, so the suitable power of the area divided by a suitable power of the volume, so that it is a scale invariant, this is decreasing because the denominator is constant and the numerator is decreasing. It can be checked. One can consider the area preserving curvature flow, where the non-local term small h is defined in such a way that the area, so that mt is constant. And everything I will say during the talk is more or less the same. So if the area is constant, you can show that the enclosed volume is monotone increasing. So again, the isoperimetric ratio is decreasing and more or less everything I will say here for the volume preserving can be repeated almost the same for the area preserving. So the interesting thing is that in monotonicity, the isoperimetric ratio is not always true for the standard mean curvature flow, which is the first time I noticed it, I was a bit surprised because so mean curvature flow is the gradient flow of the area, so it's the most efficient way to reduce the area. Also, you know that the convex hypersurface converges to something round, so to the minimum of the isoperimetric quotient. So one would expect that it is monotone also with mean curvature flow, but that's not true. So I've not written down the computation, but if you take this kind of surfaces, so capped cylinders, and if you compute the derivative of the isoperimetric ratio, so on this surface you find that if L is not even huge, I think it already if it is greater than 4, the isoperimetric ratio gets worse initially, and which is a bit unexpected. The first time I thought about it, because we know that this eventually converges to something round, so the isoperimetric ratio will converge to its minimum value. So this is something that goes in the eventually reverses the monotonicity, but not so surprising. I mean, for short times, the cylinder will become narrower. Of course, also the caps move towards the center, but at the beginning, the curvature in the different regions is comparable. So, initially, the object is becoming more asymmetric, less spherical for small times. Only after some longer time, the large curvature on the tips will prevail, and it will become more and more spherical. And so this is what I was already mentioning. There is a well-known result by Huisken in the 80s, proved by Gage and Hamilton for the curve case, that if by a standard mean curvature flow, if you start with a convex surface, convexity is preserved, it shrinks to a point in a finite time, but after rescaling, you see convergence to a round sphere. And a few time later, a similar result was proved for the volume preserving mean curvature flow. In that case, since the convergence to a round profile happens in infinite time, so there is no singularity, it exists for all times, and there is convergence as time goes to infinity. And but at the beginning, so when you look at those papers, it doesn't seem that exciting. I mean, the proof was somehow similar with adaptations due to the volume preserving term. So it just seems that you are generalizing to another flow, similar ideas. Nothing very different is going on. So for some, I think even when Esther started her PhD, it wasn't clear if how interesting could the volume preserving flow could be. Probably I'm not mentioning it here. It's a very important application was in general relativity in a paper by Huisken and Yao, where volume preserving mean curvature flow was used to construct a CMC foliation. And in that case, it was essential to use the volume preserving because we couldn't shrink to a point and rescale to construct a CMC surface in a Riemannian ambient space. But what I will show is that in more recent times, there have been cases, so when you pass to more general speed, at least some of them, volume preserving is behaving better. So, so let me mention briefly, what was the, so Wiscon's original proof was quite long, many ideas, but the starting idea was, so the general idea inspired by Hamilton's work was to control the curvature pinching. So to show that this quotient basically becomes closer and closer to 1 with the flow. And the way Wiscan did it was to consider a suitable function of the curvatures, which attains its minimum when all curvatures are equal. And in his case, the function was this one. A square is the sum of the squares of the lambda, but you can just written in this way. This clearly is 0 if and only if all lambdas are equal. And Wiscan estimated from above certain perturbations of this function. And this was the very rough idea of his strategy of proof. If you consider a different speed of the curvatures and you want to use similar techniques, so using some pinching functions, some function controlling the pinching, you immediately notice that there are non-trivial analytical difficulties, so that you can only repeat the same kind of arguments if the speed is homogeneous of degree 1, or if you assume that the initial data is not just convex, but already has some suitably strong pinching. So not just lambda 1 greater than 0, but lambda 1 greater than certain amount of lambda n, which is suitably close to 1. This, for instance, in this spirit, there was a paper with Esther and myself on mean curvature, volume preserving powers of symmetric polynomials as a speed. So otherwise, the monotonicity doesn't work. There are some bad gradient terms which are impossible to estimate when one tries to repeat the strategy. In the mean curvature flow case, there have been other techniques alternative to Wiscan's original one to prove convergence to a round point, which are based, for instance, on monotonicity formula and the classification of shrinking solutions, or more recently by Andrews non-collapsing estimate, but they are even harder, if not impossible, to generalize to flows to speed different from the mean curvature. So this is a direction I will not mention in the following. Instead, okay, so this is again what I was saying. What is this is a brief summary of what is known about generalization of Wiscan's result for general speed. So as I was saying, so part 1 is the shrinking to a point without making singularities before shrinking to a point. So shrinking to a point is known under very general hypothesis on the speed. But what is mostly unknown is whether the asymptotic profile is round, because you could also shrink to a point with a profile which is becoming less and less round. You could have something, an ellipsoid, which is shrinking with the ratio between the radii larger and larger. So shrinking to a point is a very weak property. Knowing that the profile becomes round is much stronger. And knowing that the profile becomes round is known for large class of speeds homogeneous of degree 1, and or for, as I was saying, very generally for the speed degree larger than 1 of homogeneity, but with a strong curvature pinching assumption of the initial data. And for the two-dimensional case, there are certain choices of the speed where Oliver Schnur proved the convergence to a round profile. And then so quite sensational result, and later was the complete understanding of the Gauss curvature flow and its powers. So I'm just giving the names of the ones who gave the last contribution, but it came after a series of progressive improvement. So for the Gauss curvature flow, it's completely understood. Well, I mean, it's understood that over a certain threshold, you have homogeneity, that is n over n plus 2, so something slightly less than 1. You have convergence to a round profile. When it is equal to that power, it's sort of a critical power where you have shrinkers which are ellipsoids. So then you don't, if ellipsoid is similar, then you don't converge to a round profile. And I think it's not yet known, but it's expected that for lower values of alpha, there is instability. So the becomes less and less round when it shrinks to a point. And this has been shown by Ben Andrews in the curve case. So this can be regarded as the one-dimensional case of the Gauss curvature. Of course, all curvatures are the same in one dimension. And then it is known that if the homogeneity is less than 1/3, which corresponds to n divided by n plus 2 in when n is equal to 1, it's definitely false, the convergence to a round point. And otherwise, as far as I know, it remains an open problem, even in very simple natural case. For instance, if you consider convex hypersurface with no strong pinching assumption, you consider dimension strictly greater than 2, so even h to the square. So maybe the first nonlinear generalization of the mean curvature you can imagine. As far as I know, it's unknown if you have, so you know that if you shrink to a point, but you don't know if the asymptotic profile is always round. So this is for the standard flow. What I'm going to tell is that everything becomes simpler and easier if one considers for the functions of H the volume preserving counterpart. So the result I will present, so the model case is powers of H. So you can think of phi as H to the alpha for a general power alpha. But so the power-like structure is not necessary. Well, what's necessary is having some monotone function of H with a strictly positive curvature, going to 0 as the curvature goes to 0, going to infinity as the curvature goes to infinity. So the result I present, there are other technical assumptions I'm not writing here, but are satisfied in most of the examples you may think of. So the powers, but they're not connected with growth. They are also satisfied for some exponential growth or for some logarithmic growth. So for fairly general class of nonlinear function of H, then the results, so in collaboration with my former PhD student, Maria Chiara Bertini, we consider the volume preserving flow. So we consider that the local speed given pointwise by this nonlinear function of H, plus this non-local term only depending on t, where phi bar is the average of the speed, like in the other cases. Then we have the result we expect. We hope for that there is a global existence, no singularity, and a smooth convergence to a round sphere. And so the technique of proof is at the end quite simple. It basically puts together ideas which were present in the previous literature, and basically the main observation was to show that putting these techniques together, one could attack also more general speeds. So the previous papers were did not do this remark, although all the ideas were there. First I show you that also in this case we have the monotonicity of the area, like when phi of h is equal to h. Well, one can do again a simple computation. So the derivative of the area, it's the speed times the mean curvature integrated on the surface. Then you can rewrite this quantity in such a way that you see that it has a sign. So our, I think there is a misprint here. So we have phi bar is the average of phi. Then what I wanted to say is, let me define h bar such that phi of h bar is equal to phi bar. You can find a unique value because phi is strictly monotone. So you can regard the average of phi as phi computed in something which is close but not necessarily equal to the average of h. So I mean, then we can just rewrite this. I can rewrite phi bar as phi of h bar. I can add this extra term here because its contribution has a zero integral, because this has a zero mean multiplied by constant gives a zero contribution to the integral. And when we write this quantity in this way, you see phi of h minus phi of h bar times h minus h bar. Since phi is monotone, the integral is positive. So we have a minus sign in front, it's negative. So again, we have something negative, strictly, which can only be zero if h is constant. So we have the same structure as in the basic case of the phi of h equal to h. So this first ingredient is here. So we have a monotonicity of the isoperimetric ratio, and then we can use a lemma that Wisken and myself proved in another context, and it deals with inner and outer radius. So omega is the region enclosed by our surface. Well, it's a standard notion in convex analysis. Can be defined also for a general body, but it's mainly useful for convex bodies to consider the largest possible ball inside and the smallest possible ball outside, and call rho minus and rho plus the radii. Then it is fairly easy to see that if you have a bound on the isoperimetric ratio, you also have a bound on the ratio between outer and inner radii of our body. This uses convexity, this implication, otherwise it would not be true. And so somehow what follows, we can replace the pinching of the curvatures, which we are not able to prove at the first step, with the pinching of the radii, which is something somehow weaker, but it will turn out that still will be enough for the purposes. Once you know that the radii are pinched, since the flow is volume preserving, you also know that they are uniformly bounded from above and from below. Because since they are pinched, If one of the two approaches zero, then the other also does. If one becomes unbounded, the other is also unbounded. But this is in contradiction with constant volume. If you have constant volume, you cannot have that both radii go to zero or both radii go to infinity. So they have to remain between two fixed constants. And then this is enough to let a well-known machinery in this concept to work. We can apply, there is this general principle called based on an argument which is sometimes called a choose trick, because it was first introduced by Kai-Zing Chu in a paper on a Gauss curvature flow. And the general idea, which is very flexible, it applies to large class of speed functions. And the idea is, if you have a uniform bound on the inner radius, then you can apply this argument to show that the speed of the flow is bounded from above. Because one can consider this function, so the numerator there is a speed, in the denominator there is this expression including, this is basically the support function. You pick a point which in a convex body you will typically choose more or less in the center of the body. And in our case, we pick P0 to be the center of a ball realizing rho minus. X is the position vector, and then one has this scalar product is greater than rho minus. We know that rho minus is uniformly positive. Then we can choose C0 small enough so that the denominator remains uniformly positive. Then an easy maximum principal argument shows that this quantity is bounded from above. And since the denominator is bounded from below, then the speed is bounded from above. Phi is monotone, then if phi is bounded from above, h is bounded from above, we are on a convex hypersurface. Maybe I forgot to mention, there are, or maybe it was written in a previous slide, there are classical techniques from previous work that show that even for this class of flow, convexity is preserved. So we know that our surface is convex. So a bound on H implies a bound on the second fundamental form. There is here a technical point which I'm not describing in the slide, that is the fact that P0, so the center of the ball realizing rho minus in general may move with time. And this in principle may create problems, but there is a standard way from the previous literature that can be used to circumvent this problem, so I'm not mentioning it. Okay, so curvature bound is basically the most important step to prove convergence. And then so the other concern is what I was mentioned, to show that lambda 1, lambda n do not approach zero. There is an easy estimate, well, easy with correct tools which were introduced in alternative methods by Schultz and Andrews, to show that lower bound on the curvature, which holds on compact time intervals. This shows that you don't lose convexity on finite time intervals, and this means that what we know gives a long-term existence of the flow. Then we would like to show convergence to a sphere. There is apparently, there is a potential problem to show that this lower bound is uniform also as time goes to infinity. Because while in the contracting case, the minimum of H, it's easy to see that it is monotone increasing. In a volume preserving case, it potentially decreases, it may converge to zero in infinite time. if you just look at the equation. And this may be a problem because recall the case we have in mind is h to the alpha, and if h goes to 0 and alpha is different from 1, the derivative either goes to 0 or to infinity, depending alpha greater or less than 1, and this gives problems to regularity. And this was already encountered by Felix Schulze in standard flow without volume preserving term, and he used some sophisticated estimate from porous media equation. But we, in the volume preserving case, we noticed that it's possible to use a variant of choose trick, just reversing signs and using enclosing balls instead of enclosed. And by sort of magic, this gives a lower bound on the speed. And the interesting fact is that the dominant term when we do the maximum principal argument is the one with the volume preserving term, which in the other part of the argument is just a term which is neglected. But in this case, it's the dominant term, and this shows that the argument could not be applied in the non-volume preserving case, in the standard flow. So it's another nice feature of the volume preserving case. And then once we have a positive lower bound, you recall, we know that the area is monotone and that the derivative is strictly negative unless the curvature is constant. Oh, again, this is a misprint. What I wanted to show here is that this derivative goes to 0. We have a positive function decreasing, defined in an infinite time interval. Well, this could be an easy mistake of a calculus class to say, oh, monotone decreasing function with bounded from below, then the derivative must converge to 0. In general, it must, it may not be the case, but if we have enough regularity to show, for instance, that the derivative is uniformly continuous, then it must converge to 0. So what I wanted to write there is the derivative converges to 0 as t goes to infinity. But this also shows, implies that the curvature minus its mean value must go to 0 uniformly, and then standard methods employing parabolic regularity yield convergence to a round sphere, and this concludes the proof. And let me, so I forgot to write a slide. This has been later generalized, so in a very partial form by myself and Bertini, and instead in a complete way by Andrews and Yongwei for not just powers of H, but general powers of HK, so the kth curvature, the kth elementary symmetric polynomials of the curvatures. So any elementary symmetric polynomial, any positive power regardless homogeneity greater than 1, less than 1. If you consider the volume preserving flow, you have convergence to a round sphere, which is considerably more difficult because when most of the argument applies, but then so strict gives this time only an upper bound on the kth symmetric polynomials of the curvature, and this does not directly imply a bound on the second fundamental form. So the method becomes considerably more complicated. Okay, then I will skip to the other two cases, which I will describe very briefly, and maybe I will draw a quick picture. Okay. This setting we consider hypersurface with contained in the upper half space with boundary in the on the space where the n+1 coordinate is equal to 0, and we have a prescribed angle on the boundary. And so just to fix the notation, I call M the hypersurface. I call omega the enclosed domain. This is a different notation from the one which is in the paper, but I wanted to. And then I think sorry, again I put the wrong letter. So the capital sigma in the last line should be all M. I apologize. So I call the contact surface, I call tilde M. So the enclosed region is omega, and it has as a boundary our surface M, and this contact surface tilde M. And this is the boundary of our evolving surface. Okay. Then one can adapt the definitions of the closed case. So instead of considering the Euclidean area of M, it's more natural to consider this expression. So the Euclidean area minus the area of this contact region multiplied by cosine theta, which can also be regarded as an integral of that expression on M. Then one can define the capillary version of the isoperimetric ratio, replacing the usual area by the wetting area. And it turns out to be the correct definition in the sense that there is a isoperimetric inequality. This is minimized, so it's when the surface is completely spherical, so it's the intersection of a sphere with the upper half space. So when it is completely round, of course, with the same rectangle. And then the result we are looking for is to show that a general convex M with this structure with our flow converges to a spherical cap with the same volume if we do volume preserving. So how do people study flow in this setting? You understand, if we flow in normal direction, then we break the constraint of our surface. So people have studied this flow by changing the normal, define this modified normal called capillary normal, where so it turns around. So this is defined in such a way that so nu would be this, but the nu tilde is this one. So it is horizontal. So the nu tilde turns, it's the nu pushed above by a certain fixed quantity. And the quantity is chosen in such a way that along the boundary it makes nu tilde horizontal. And then one can consider this flow with this modified normal, and I will describe the result when the speed, the local part of the speed is the power of h as before, and there is this small h written down, it's the average of h to the alpha with prescribed boundary condition throughout the flow. And it's so standard results on boundary problems show that the problem is well posed, there is a local smooth solution. Then there is this result with Liang-Jun Wang, now postdoc. So he did his PhD in Freiburg and is now postdoc in Pisa. And he, with Guo Feng Wang and Xia, so there is a group of people who are extensively studying curvature flows of capillary surfaces. And so I learned the techniques, the capillary machinery from him. And so we put together our expertise to attack this problem. That the same result I described above hold in this case. We have if the angle is acute, so less than p half, we have convergence to a round profile, which is a spherical cap in this case. And just a remark on the statement, if the case theta equal to p half could be reduced by the closed one, just continuing by symmetry the hypersurface, so it would not be new. And if we have obtuse angle, we expect that the result does not hold, so that this is not just at the first sight, it may look a technical definition. We need a certain sign of cosine theta in certain maximum principal arguments, but we expect that, so with an obtuse contact angle, we may have something like this, which may possible develop a neck pinch on the contact surface. So the result may be false in general. And so I just described the basic idea is that we can adapt the technique I described you before. So the capillary isoperimetric ratio is decreasing, so the sweating area is decreasing. Then one can make a capillary analog of the radii pinching. So we consider the radius not of the enclosed sphere, but of the enclosed spherical cap. And again, the bound of the isoperimetric ratio implies uniform pinching of the capillary radii. And then the whole strategy applies, and we I just noticed that there are some extra difficulties since every time we apply the maximum principle, we need to control what happens on the boundary, which was not present before. But for this kind of speed, it is feasible. We have tried the other speeds where this instead is more complicated, so we don't know yet how much this technique can be generalized. And yeah, the next thing I would wanted to mention is the fractional curvature, but I don't know how much time I'll create. Oh, okay, maybe. Okay. So so I'm usually not working on non-local fractional operator, as I guess most of you. And when I see usual fractional operator with this integral singular quantities, I feel unfamiliar. But the fractional curvature, I saw it in a talk by Xavier Cabré in Rome. Maybe, yeah, now it's something like 10 years ago. And I think it's nice. It has a nice interpretation. So you see there is this integral where you have a singular kernel. This is even a divergent function because of the power, but you consider it with the opposite sign. This is characteristic function with opposite sign in the set and in the complement. So basically you make the difference of the contribution in the set and the contribution in the complement. So maybe I will not draw a picture, but what shows is, or maybe you have your set omega, you have a point, and somehow you see by symmetry, if it is convex, for instance, all the contributions from here will be cancelled by the contributions from here. So actually, you're only integrating here. So you see that if it is regular enough, you have better convergence properties that make this integral finite. And also that in the picture I've drawn, the complement wins. On the complement, we have a positive sign, so this gives a positive curvature. I mean, at least the contribution here is positive. Then you have the contribution of all the rest, which can have a different sign. And so let me go very quickly. This has an interpretation, as in the classical case, as first variation of a suitable non-local perimeter introduced by these authors. There's also parametric inequalities, characterization of CMC surfaces. And so what's known about the fractional mean curvature flow? Not so much. So it's really a hard problem in general. The first results were for weak solutions, was the reversed order with respect to the classical case. Then eventually also for classical solution. There is invariance of convexity. There is a paper with some qualitative property by Mariel and Baldinoshi. Some problems are completely open, like Wiskan's result, where the convex sets converge to a round point. I know people have tried to derive a monotonicity formula, but without success until now. And but what is true is again convergence to a round profile of the volume preserving mean curvature flow. So to go very quickly, me with Eleonora Scinti and Enrico Baldinoshi basically reproduced the same strategy of proof I described you before. In this case, this was not the whole story because basically we didn't know that if, in this case, if the curvature is bounded, then the smooth solution continues to exist. So basically we did some estimate and we said, well, if the solution exists, then it goes to a sphere, but we had not enough to justify this claim. Was so a partial step, but it was eventually justified by Yulin and Lamanna, who filled the missing parts in our procedure. And so also in this case, we have convergence to a sphere. So in this case, it is known in the volume preserving case, but unknown in the standard case. So sorry for being a bit late, and thank you for your attention.
Are there any questions? You mentioned the case of the power of the flow by Gauss curvature.
Yeah.
Said that some ellipsoids are 3%.
Yeah.
They all ellipsoids or just some ellipsoids?
I think all ellipsoids. So I think that there is something I never understood well. There is this affine geometry. I think this critical power is affine invariant. So the flow is invariant by affine transformation. So since an ellipsoid is affine, can be transformed into a sphere by an affine transformation, and sphere is homothetically shrinking. Also for that power and for the Gauss curvature flow, ellipsoids are, I think all ellipsoids are, if I remember well, are homothetically shrinking.
Maybe you said something about that, but I missed it. What in principle one use is convergence result, for example, in this capillary case, but also in the classical case, to prove the Euclidean or the capillary perimetric inequality, or somehow you need this perimetric inequality to run this kind of argument?
So think we don't really need maybe just some bound on the isoperimetric ratio, which of course is much weaker than the isoperimetric. But in principle, yes. In principle, this is a proof of the isoperimetric inequalities for these convex smooth objects, which of course is a very restricted class. But so the hope is that these kind of ideas could be used for finding new isoperimetric inequalities. Not in the setting I have described in this talk, but there are some, for instance, I think I don't remember if it is volume. There are some specially designed flows by Guan and Li, where they proved so they extended some isoperimetric, some Minkowski inequalities, which are known in the convex case for something like something weaker, like kth curvature positive. So what I've described here has only weak applications, but weak in the sense to reprove something well known. But this kind of ideas, hopefully, with other flows, can lead to new non-trivial isoperimetric inequalities.
Okay. But what you get for the limit shape is somehow you directly get that's the sphere, or you find that it's a sphere after you get
no. We get that it is a sphere again because
you don't use that
because if so to say, it's only a stationary point for the Lyapunov functional. So
okay, this is how you get the sphere.
Yeah.
Okay.
Since if it converges to something else, then you would not see that you would have that the derivative of the area converges to something negative, which is impossible because it is incompatible with being bounded from below.
Questions? Then, if not, so from the speaker again.